Hello, good morning. My name is José Alejandro Montes Ballinas. I'm a master's student from the Universidad de Ciencias y Artes de Chiapas, and I'm presenting the results of my research, minimum entropy generation in a magnetohydrodynamic flow of a hybrid nanofluid through an inclined channel, effects of internal heat generation, Brownian motion, and thermophoresis. This work focuses on the optimization of magnetohydrodynamic flow of a hybrid nanofluid composed of aluminum oxide and copper nanoparticles in water under various physical effects. The main objective is to minimize entropy generation and improve exergy efficiency, which are essential for designing more energy efficient thermal systems. We consider a fully developed laminar and two-dimensional magnetohydrodynamic flow of a viscous and incompressible hybrid nanofluid moving between two flat parallel and permeable plates separated by the distance a. The model is formulated within the frameworks of the Darcy-Forchheimer flow regime and also incorporates the effect of coupled stress. The bottom plate of the channel is in contact with the head source hot fluid, while the top plate is assumed to be exposed to ambient environment. The nanofluid is injected uniformly through the bottom wall, while suction occurs through the upper wall. Hydrodynamic slip conditions are imposed on both plates, enabling a more realistic representation of interfacial effects in microscale systems or surface with low roughness. The thermal analysis includes the effect of nonlinear thermal radiation modeled using the Rosland approximation, as well as terms associated with viscous dissipation and ohmic heating, resulting from an interaction between the magnetic field and conductive fluid. Additional mass transport mechanisms such as Brownian motion and thermophoresis of the suspended nanoparticles are taken into account. It is assumed that the nanoparticles are base fluid are in local thermal equilibrium and move with the same average velocity, which justifies the use of a single-phase nanofluid model. Dimensionless mathematical model. This set of assumptions allows us to formulate system of governing equation. Momentum balance equation. This equation describes how the different forces acting on the fluid affect its motion. Each term has a specific physical meaning. The most important for us is U, that is dimensionless fluid velocity. Theta is the dimensionless temperature profile, and phi is the dimensionless nanoparticle concentration. Energy balance equation. The energy equation describes how the heat is transferred within the flow. Mass concentration equation. This equation describes how the nanoparticles are distributed within the fluid. Entropy generation. Local entropy generation in magnetohydrodynamic flow of a hybrid nanofluid within the inclined channel arises as a result of various irreversibilities present in the systems. Here, the terms respectively present the entropy generation associated with heat transfer by conduction and thermal radiation, Brownian diffusion, thermophoric diffusion, viscous dissipation, Darcy friction, Forchheimer friction, ohmic heating, coupled stress. Heat transfer, nozzle number. Heat transfer in microchannel is evaluated through the nozzle number, which represents the ratio between total convective transport and pure conduction. Considering the presence of nonlinear thermal radiation, the local Nusselt number can be defined as follows. Friction coefficient. The surface friction coefficient represents a form of drag that acts as resistance to the movement of the nanofluid contact with the walls of microchannel. As this coefficient increases, so thus the energy is required to maintain a given flow rate. Therefore, system performance improves when this resistance is reduced. The friction coefficient is defined based on the shear stress at the channel wall, as expressed below. Mass transfer. Mass transfer in the system can be quantified using the dimensional shear wave number, which represents the ratio between convective transfer and diffusive transfer of matter. This number is analogous to Nusselt number in heat transfer and allows for the evaluation of the efficiency of the nanoparticle diffusion process in the nanofluid within the channel. Data analysis. In the figure 2 shows that as gamma increase, the velocity of the nanofluid increase throughout the entire domain. Since gamma represents the inverse of the intensity of the coupled stress in the porous medium, lower value of gamma correspond to greater internal resistance to flow due to increase in effective viscosity of the nanofluid. This increase in resistance leads to greater viscous friction with the channel, thereby reducing the velocity magnitude in the profile. Figure 3 shows that the parameter Rd increase, the temperature of the hybrid nanofluid decrease throughout the entire domain. This is because a higher value of Rd intensifies the effect of nonlinear thermal radiation, which promotes greater dissipation of thermal energy toward the channel walls. As a result, the system loses heat more efficiently, leading to the lower temperatures profiles. On the other hand, when Rd there is no contribution from the radiative term in the energy equation, which causes thermal accumulation in the system and a higher fluid temperature. Figure 4 shows that the thermophoresis number increase, the concentration of nanoparticles in the hybrid nanofluid decrease throughout the entire domain. This behavior is due to the fact the higher NT intensifies the thermophoretic effect, that is, the transfer of nanoparticles from high temperature regions toward colder regions. This migration reduces the amount of disappear phase rating locally, causing a decrease of nanoparticle concentration increase. In figure 5, the behavior of local entropy generation S show for different values for the nonlinear thermal radiation parameter Rd. It's observed that Rd increased the local entropy profile increased significantly throughout the domain. This is because a higher value of Rd intensified the effects of the thermal radiation in the system, which increased the rate of thermal energy transfer by radiation. As a result, large temperature gradients are generated, with in turn increased thermal irreversibilities and consequently the local entropy generation. A figure shows the behavior of local number nozzle at y equals 0 as functional of parameter gamma, which represent the inverse of the coupled stress. Although the monotonic trend might be expected, the graph displays an irregular oscillation with slight increase and decrease between nearby values, particularly at gamma equal 0.7 and gamma equal 0.9. This behavior may be attributed to the sensitivity of the thermal gradient near the wall to a small variation in gamma, as this parameter affects both the velocity distribution and the system viscous dissipation. As gamma decreases, the effect viscosity of the nanofluid increases, which reduces velocity and consequently the convective transport rate. However, the couple between velocity, temperature profile, and head flux near The wall can induce regions of non-linear behavior, generation small fluctuation in the temperature gradient, which is presently what defines the value of a nozzle. Furthermore, it's possible that a shooting method is used to solve this system is capturing micro variation in the thermal gradient with high precision, resulting in slight jumps in the curve. In figure 7, show the behavior of the skin friction coefficient at y equals 0 with respect to nonlinear thermal radiation parameter Rd. In general, the curve exhibits a non-monotonic trend with localized peaks around Rd equals 0.1 and 0.9. This peak can be attributed to adjustment at the thermal viscous equilibrium near the lower wall. As Rd increases, the temperature field is affected of nonlinear manner, subtly modifying the velocity gradient and consequently the surface friction. Conclusions. The inverse coupled stress parameter gamma significantly influences fluid velocity and entropy generation. Lower gamma increases viscous resistance and reduces entropy. 2. The thermal radiation parameter Rd enhances heat dissipation, increases entropy generation, and alters temperature and concentration gradients. 3. The thermophoresis parameter and T show non-monotonic effects on concentration and entropy profiles depending on transverse position in the channel. 4. Peaks and oscillation observing the friction coefficient and Sherwood number suggest traditional Riemann and nonlinear transport behavior. These findings highlight the complex coupling of thermal mass and momentum transport mechanisms in hybrid nanofluid magnetohydrodynamic systems. The results provide practical insights for development of advanced cooling systems and high efficiency thermal technologies. Thank you so much.